So welcome. My name is Bob Jacobson. I'm here from the physics department to introduce Joel. As you've seen from the movie, how many of you actually read this book? Okay. I'm going to try really hard not to give away any clear plot points. But this movie involves a certain amount of dispute between scientists and the Vatican. And I won't tell you who wins. But one of the key parts of it is scientific research that's done at a place called CERN, building something that is going to be used to do detriment to the Vatican. And Joel will tell you more about this. We take this in a very lighthearted spirit. You know, scientists have been in conflict with other cultures, even in this campus, forever. Do you know who this campus is named for? Bishop Berkeley. You know what he's famous for? Proving that the calculus was wrong. So we got even with that, although it took 180 years to finally do it. He also was a philosopher, but that doesn't count tonight. So we view this in a certain lighthearted way. As part of that, we have brought t-shirts because we're going to adapt you to our culture. And because I'm a physicist, I probably can't throw these that far. It's really tough to get a spiral out of a t-shirt. I got 2 more to go. There's no way I can hit you that far away. Okay, that's it for that. If you brought a card, if you got a card and you brought it, Maria is the person to give it to. She's waving a card right here. And Joel actually works in this. Joel works in the production of antihydrogen. He has for a while. This is an ongoing project. It's a wonderful piece of science. He has to leave tomorrow morning to go to CERN, which is in Switzerland, to work on it. So we thank him in advance for spending his evening with us, telling us all about it. Over to you.
Well, thank you very much. I'm sorry about us getting started late. We've set up a large number, well, a few demos here, and they've taken a little bit of time to get running. I think I'm a little bit too loud at the moment, so. No? Okay. Sounds too loud up here anyway. Okay. As Bob just mentioned, the book, Angels and Demons, this movie, Angels and Demons, is based on this book by Dan Brown. And the most I'm going to give away of the plot in a big way is that the plot is that a secret society called the Illuminati steal about 1/4 gram of antimatter from the CERN physics laboratory in Geneva, Switzerland, for use in a plot to blow up the Vatican. And fortunately for us, Sony Pictures has been kind enough to provide us with a clip which explains all of the physics behind this, which I'm going to play for you. This is quite quiet, so I'm going to turn the volume up.
Where is that camera number 86?
It's wireless. It too was stolen. It could be anywhere inside the Vatican walls.
That canister contains an extremely combustible substance called antimatter. We need to locate it immediately or evacuate Vatican City.
I'm quite familiar with incendiaries, Miss Vetra. I've never heard of antimatter being used as such.
Well, it's never been generated in significant quantities before. It's a way of studying the origins of the universe, to try to isolate what some people call the God particle. But there are implications for energy research.
God particle?
What we call it isn't important. It's what gives all matter mass, the thing without which we could not exist.
You're talking about the moment of creation.
Yes, in a way I am. The antimatter is suspended there, in an airtight nanocomposite shell with electromagnets on each end. But if it were to fall out of suspension and come in contact with matter, say the bottom of the canister, then the 2 opposing forces would annihilate one another violently.
And what might cause it to fall out of suspension?
The battery going dead, which it will, in 6 hours.
What kind of annihilation? How violent?
A cataclysmic event. A blinding explosion equivalent to about 5 kilotons.
Vatican City will be consumed by light.
Got that? I hope you understood that, because to tell you the truth, I haven't a clue what they were talking about. All right, that's not really true. I do understand some of this stuff. A physicist, a Nobel Prize-winning physicist named Leon Lederman, decided to call a particle known to physics as the Higgs boson, he decided to call it the God particle. Well, actually, he didn't. His publisher did. He wanted to call it the goddamn particle, which got censored. But you have to agree that they have different implications. Nonetheless, the God particle got taken up by the media. Physicists hate it. We refuse to acknowledge it, but there it is. The Higgs particle, or the Higgs boson, was proposed by Peter Higgs and others back in the 60s. And the Higgs is the only as yet unobserved particle in the standard model of particle physics. It's a very important particle because it's this particle which is thought to give mass for all of the other particles. We've got electrons, protons, neutrons, and so on and so forth, but we don't have any fundamental understanding of where their mass comes from. In fact, they all scale off of this Higgs particle, and if we could discover the Higgs particle, we would be able to predict what the mass of all of these particles are. So it's a very important particle, and at this point, detection of the Higgs is probably the goal of particle physics. The search for the Higgs actually began at some level here in Berkeley with the discovery of the accelerator or the cyclotron, the invention, I should say, of the cyclotron by E.O. Lawrence back in 1931. The very first accelerator that was built here was 4.5 inches on a side, about this big, and could accelerate particles up to about 80 kilovolts. Not very much, but pretty soon we went over to the 37-inch cyclotron, which could get particles up to 8 million electron volts. Actually, many of you have seen this device because it's currently sitting up at the Lawrence Hall of Science in the parking lot. Who's seen this thing here? Many of you have. It doesn't look like very much nowadays, but it was a truly important device in the history of physics. After the 37-inch cyclotron, there were a number of others. But before I go to some of the others, let's just talk for a moment about how much 8 million volts is, which was what the 37-inch cyclotron could get us to. 8 million volts is about 70,000 times the voltage in a 120-volt outlet, to give you some sense of scale. To go to perhaps a higher scale, it's 16 times the voltage on the Pacific intertie, which is one of the 3 main interties that brings power from the Oregon and Washington reservoirs down to Los Angeles to be used in air conditioning down there. So 8 million volts is much, much bigger than you find on even the highest common system that that's commonly available. So it's really remarkable that you could get to that kind of voltages in such a small system. But it wasn't enough. Physicists are greedy. So then they went to the 184-inch cyclotron, which was built in 1942. You can still see parts of this. At least you can still see the building that houses this thing. As you go out of here, if you look up at the Lawrence Berkeley National Lab, you can see this dome at the top. And the 184-inch cyclotron was built inside of that. The final cyclotron, or I should say the final big accelerator built here at Berkeley, was the Bevertron in 1954. This was 100 meters in diameter and could get up to about 6 billion electron volts. Unfortunately, this was the end of the line here in Berkeley, and the reason is that, well, 100 feet is really very large, right? And people realized that sticking large accelerators on a very steep hillside in a fire zone a few hundred meters from a major earthquake fault really wasn't such a great idea. Now, in building these sorts of accelerators, they had to change the shape. The original ones were just solid disks, but you couldn't build a solid disk which was 100 meters in diameter, so these accelerators became donut-shaped. And what would happen is you'd have particles that were going around and around inside of these accelerators. And every time they would pass a certain place in the accelerator, they'd get a little kick. So they'd go around faster and faster and faster and faster. Well, once the effort left Berkeley, it went to lots of other places. The biggest accelerator in the world at the moment is the Tevatron, which has a ring which is 3.9 miles in circumference and can get up to just about a trillion volts or something like that. But very shortly, perhaps later this year, the accelerator called the Large Hadron Collider at CERN should come online. This is in Geneva, Switzerland, and you can't see it too well on this photograph, but you can see there's this huge ring going all the way around. It's 17 miles around. To give you some idea of the scale of this device, there are no roads that go straight across. So if you take a bicycle, you have to wander around a little bit, but it takes about 30 minutes to bicycle from one side of the ring to the other. Now, CERN itself is a huge institution. There are about 10,000 people associated with it at the moment, from about 500 universities in about 80 countries. If you take a look at my badge over here, my badge is 91,666. Let's not wonder about why I'm 666. But the implication of this is that there's been almost 100,000 people associated with this laboratory over the years. Now, there are 20 official member countries. These are the closest members in there. Unfortunately, the United States is not actually a member of the CERN laboratory, despite us giving them about $1 billion in recent years. This means that we don't have full privileges at the laboratory. One of the privileges, for instance, that we do not have is we are not actually allowed to fly our flag in front of the laboratory. But anyway, this laboratory has this 17-mile tunnel, and inside of that tunnel, there's this huge accelerator. This accelerator and the detectors associated with this accelerator cost about $10 billion, which is really a huge amount of money, no matter how you look at it. But physicists really do expect to be able to detect this Higgs particle, or the God particle, if you insist, at the LHC. Because of that, parts of Angels and Demons were filmed at the LHC and at the Atlas detector. Here's one of these detectors, which is used for figuring out what happens inside of this accelerator. To give you some idea of the scale of this project, when this thing is fully operational, the amount of information that will be generated by this detector will be about equivalent to the total worldwide telecommunications traffic. And all of that is coming out of one little space, which is a really astonishing thing. Well, anyway, the cast was at this place, and Tom Hanks and Islet Zur were photographed, and everybody was very happy to be seen with stars and things like that. Not me. I wasn't there at the time that they filmed this. But really, what do all of these big accelerators have to do with using antimatter to blow up the Vatican? Well, the answer is not very much past the Bevatron, the last big accelerator that was built here at the Berkeley labs. To understand antimatter as it's actually used in Angels and Demons, we need to consider charges and particles, to go way back to the beginning, in fact, to Benjamin Franklin, who postulated that there were negative and positive charges. And we now know that these charges, Franklin's charges, are typically carried by electrons and protons. Electrons are negatively charged and protons are positively charged. Put them together in a really crude and sort of embarrassingly simple model, and you have a hydrogen atom. Add a few more protons and electrons and some neutrons as well, and you can build up our entire periodic table of normal matter. The anti-electron, or the positron, was a prediction by a famous physicist named Dirac, who in 1928 had a problem with his mathematics. It blew up. And to solve this problem in his mathematics, he invented a positive electron. It seems like a hoax, but in fact, it turned out to be correct. And this positive electron the positron, as it's now called, is simply the charge swapping of an electron. So take an electron and change its charge from negative to positive, and you'll get a positive electron or a positron. Aside from the change in sign, positrons are believed to be otherwise identical to electrons. Well, this wasn't just a phony thing. Very quickly thereafter, they were discovered 4 years later by a guy named Carl Anderson, who discovered them in cosmic rays. And here's a photograph of a positron, one of his originally detected positrons, going through his apparatus. What are positrons from cosmic rays? What are cosmic rays? Well, the top of our atmosphere is constantly bombarded by highly energetic particles. Most of these particles come from outside of the solar system. They come from other stars, perhaps even other galaxies. And they move so fast that when these particles come in and hit, say, an oxygen molecule at the top of our atmosphere, they split the nucleus of that oxygen molecule. In fact, not only do they split the nucleus, they split the things that are inside the nucleus. And you get a shower of different particles that come out. In this depiction, this proton is turning into several different types of pions. And these pions themselves, which are a very strange sort of particle, are themselves hit other nuclei, and they split, or they spontaneously split all by themselves into yet more particles. And the net result is that we get a shower of particles coming down from every proton that hits our upper atmosphere. Here's a depiction of such a shower. One proton comes in, and it creates initially maybe 2 or 3 other particles, and each of these particles split again, creating more and more particles, so that we wind up with an enormous number of particles down here at ground level. In fact, as you sit there out in the atmosphere, there are some of these cosmic rays coming down and going right through you, particularly a type of particle called a muon. And there are approximately 1,000 muons per second coming down and hitting you, going right through you at the moment from these cosmic ray showers. Now, there are also naturally occurring sources of positrons. There's an isotope of potassium, potassium-40, which is very commonly found in things like bananas. And this is a rare but not that rare isotope. About 1 atom in every 10,000 of potassium is potassium-40. And potassium-40 emits positrons. It emits antimatters. So as a result of eating this banana, over the course of time that this banana and its constituents, its potassium, stays in me, I will experience approximately 1,000 or so positrons inside me, which suddenly go out. Now, of course, if you have more bananas in you, you'll get more positrons. Oh, where's the sound here?
Then begin to talk about the Christmas tree. I hope that means that everyone is glad to see the lady in the tutti frutti hat.
Well, anyway. Nowadays, we can make artificial sources of positrons. In fact, I have to stop eating this banana. So only about 500 of positrons will be emitted inside of me. One of the most potent artificial sources of positrons that we can make, and by the way, we make these by transmutation of elements inside of other accelerators, but one of the most potent ones is an isotope called sodium-22. And I was actually able to borrow a sample of sodium-22, and it's inside here, inside this bubble chamber, emitting positrons, which unfortunately I'm not really seeing at the moment. But what we were going to show you is some tracks of positrons coming out of this device. This is all set up, right, Rupert? Well, it's about as working as well as it's supposed to. I see all sorts of other things coming in here. Actually, you guys can take a look at what's coming in here, perhaps. If we could have the camera on the auxiliary video. Is this working? Are you seeing this camera over here? Oh, it's camera 3? Yeah. Okay, most of what you see there are not particles, but every now and then you should be able to see a streak that goes through this image. And those streaks are mostly cosmic rays. But our sodium source of positrons is this thing over here. And if you look really closely, at least before the lecture, when this was working an hour ago, you could see that there were positrons being emitted by that source. And you could see the tracks left behind from those positrons as they go through. But unfortunately, I'm just not seeing them at the moment. If you want to come up after the lecture, this may be working by that point. Sometimes it takes a while for this to get going. I apologize for that, but we're just going to have to move on. Okay, the artificial generation of positrons has become quite important lately in the medical profession because we can use positron emission tomography to learn a great deal about what goes on inside people, especially sick people. What happens is that you are forced by your doctor to drink or breathe, or you have injected into you some radioactive isotope that emits positrons, and that radioactive isotope is absorbed in various organs inside of your body, depending on whether or not that particular isotope has some particular metabolic activity for the particular isotope that I'm not saying this very clearly. If, for instance, you ingested something like iodine, it would go straight to your thyroid, right? And if it was radioactive, you could see your thyroid lit up like this. Well, in this case, you can't see this very well, but there's a person over here who was forced, I think, to have some radioactive substance that emits positron injected into his veins, and you can see that they all concentrated inside of this person's stomach. Something's actually wrong with this person. And this proves to be a very powerful diagnostic technique for doctors. Well, that's positrons. What about antiprotons? Just like there are anti-electrons, there are antiprotons. If you take a proton, which is positively charged, and swap its charge so that it's negative rather than positive, you'll get an antiproton. And just like with electrons and positrons, aside from the change in sign, antiprotons are thought to be otherwise identical to positrons, to protons. So it turns out that the very first antiprotons were discovered here in Berkeley at the Bevatron, that accelerator that I showed you a few minutes ago. They're made in a process which is quite analogous to the way positrons are made in cosmic rays. You take a beam of protons and slam them into a metal, and after this collision, a very small number of antiprotons will come off of that metal. The first ones were made, as I said, in Berkeley in 1955 by Segre and Chamberlain. Segre is the short one, Chamberlain is the tall one in this picture, and they received the Nobel Prize for this work. Now, just like today, publishing is very important, but unlike that today, they didn't have the World Wide Web to publish their results. So there's a really neat photograph of how they published their results, at least within the local Berkeley community. It's a photograph of a blackboard, which shows that on October 6th at 4:30 p.m., they had detected 38 negative particles of the appropriate mass. In other words, 38 antiprotons just at this moment. Now, if matter then is just made of negative electrons and positive protons, and antimatter is made of positive electrons and negative protons, positrons and antiprotons over here, and they're just basically swapping the charge, why would we care about all of this? What's so different about antimatter compared to matter? Well, the answer is that if you allow matter to touch antimatter, it blows up, it annihilates. And when it annihilates, all of the matter, all of the mass turns into energy via Einstein's famous equation, E is equal to mc squared. You get an enormous amount of energy out of this process. in the Angels and Demons book, about 1/4 gram of antimatter is stolen from CERN. This is equivalent to 10 grains of rice. And yet, if you took 10 grains of antimatter rice and allowed it to touch normal matter, it would cause an explosion that would be a 10 kiloton of TNT explosion. For comparison, the bomb that was blown up over Hiroshima was 15 kilotons. Now, that 15 kiloton weapon contained 64 kilograms of uranium inside of it. So the fact of the matter is that you get an equivalent size explosion out of these grains of rice, even though they weigh about 250,000 times less, as was used to blow up Hiroshima. It's truly an enormous explosion. And this would deal enormous damage to the Vatican if it was used. If we start at the Piazza San Pietro and go outwards, just to get some idea of what Vatican City looks like, and then if underneath the obelisk in the middle of the plaza I was to allow those 10 grains of rice to blow up, I would get a circle of devastation about this big. In other words, everything within this range would be gone. And there would be very, very significant damage well beyond that point. So you really could, in principle, do a lot of damage to the Vatican if you were to blow up some antimatter there. But we actually shouldn't fear for the Vatican. And the reason is that the economics associated with antimatter production are utterly and completely infeasible. Why is this? Well, antiprotons are still made the same way they were made back in the Bevatron here in Berkeley, by crashing very energetic protons into a metal. And only a very small fraction of the protons turn into antiprotons, about 1 in a million. This fraction results from fundamental physics, not technology, and is not likely to change all that much. To make a 1 gram of antimatter would require the entire world's energy production for about 100 years. Now, what do I mean by that? Everybody would have to stop cooking, driving their cars, lighting their houses, using the internet. Absolutely all of the uses of energy in our society would have to be funneled over to CERN or some equivalent accelerator for a whole 100 years, for a century, to make a mere 1 gram of antimatter. And that's looking at it on the bright side. In actual fact, accelerators, like the Bevatron, have what is called a wall plug efficiency. They don't manage to take all of the electricity that you put into them and put them into the particles. At best, they're about 10% efficiency. So our 100 years has now become 1,000 years. And things get worse than that. If you take a large number of antiprotons and put them into a small space, they don't like it. You can exactly the same effect by trying to put a large number of electrons into a small space. And in a moment, if this actually starts to work, I'm 0 for 1 from my demos so far today. All right, I'm going to cheat. In a moment, oh, this is pathetic. What happens, as you've all seen in this is a Van de Graaff generator. I'm sure you've all seen this before. What happens if you put too many of them into a small space is they like to spark. They're going to repel each other. They don't like to be all gathered together. And in fact, all of these antiprotons are going to vanish. Our ability to trap antiprotons into one small space is rather limited. And when you include that factor in, our 1,000 years becomes about 1,000,000 years. So unfortunately, or fortunately, depending on your point of view, we're never going to be able to generate the 1 gram of antimatter that would be equivalent to make a substantial weapon. In many ways, this is a real shame, because we could get to the stars on about this much antimatter. This much antimatter would take a 100 kilogram space probe and accelerate it to about the 10th the speed of light, which would be more than sufficient for sending a probe to the nearest stars. If you wanted to go to a nearest star yourself, you'd probably need a spaceship that was, say, on the size of a 747, and we could get that to go to a 10th of the speed of light with about 1,000 kilograms of antimatter. So it's a real shame, really, for at least space exploration that antimatter fuel isn't a practical thing, but the facts of economics dictate that it is. So why should we study antimatter? If aside from the sign swaps and this minor fact that it blows up, antimatter is thought to be identical to matter, why bother doing this at all? Well, there are many reasons to study antimatter. One of them is that we don't know how antimatter interacts with gravity. It's certainly well known that apples are attracted towards Earths. And everybody believes that anti-apples would be attracted towards anti-Earths. But it's an open question about what would happen to an anti-apple. Would it fall down towards Earth? Some physicists have speculated that, in fact, an anti-apple would fall up and go away from Earth. The betting is against it, but it's a possibility. It's something that people want to think about, and we have absolutely no experimental evidence on this question. There's an experiment at CERN that's trying to look into this question. It's not my experiment, it's another one. And the way they propose to do it is to fire very slow antiprotons that are moving at about 100 meters per second, which is about the slowest that we can get them, down a 1 millimeter tube. The protons will be deflected downwards by Earth's gravity. They're going to fall, presumably. The protons are the antiprotons. And they would fall by a distance of about 0.5 millimeter. This is a large distance as physics experiments go. It would be easy enough for us to detect that they had fallen such a large distance. So this sounds like a great experiment, but there's a catch. Because inside of this tube, there are electrons. In the walls of the tube, there are always going to be electrons. And if for some reason one of those electrons went from the top tube down to the bottom tube, that would create an electric field which was pointing vertically, and this electric field would be due to the charge imbalance between these two plates. Unfortunately, that electric field would also push on our antiprotons, and it turns out that it would deflect them by a distance that is more than the distance of gravity. Down this 1 millimeter tube, instead of falling by 0.5 millimeter, they would actually, the way I set it up, go up by almost 10 millimeters, which would completely swamp out the effect that we were trying to measure, because it's absolutely impossible to have the two sides of these tubes be so well balanced that there isn't even a 1 electron difference between the top and the bottom of the tube. So what could you do about this? Well, the reason the antiproton is deflected by the electric field is because it's charged. Neutral antimatter would not be deflected by the electric field and could be used to measure the effects of gravity on antimatter. What do I mean by neutral antimatter? Well, just like we can make a hydrogen atom by taking a proton and having an electron go around it, we can also make antihydrogen atoms by taking an antiproton in the center and having a positron go around the outside. This net object as a whole is electrically neutral and won't be affected by the electric fields that we could have gotten in our trap. So we can use antihydrogen atoms to measure gravity. There are yet more reasons to study antihydrogen atoms. One of the things that we would like to do with them is to look at the spectrum of antihydrogen. If you take a look at any gas and you run an electrical current through it or some other way of running, well, basically run an electrical current through it, it's going to glow. Here's, for instance, mercury gas glowing. And over here is neon gas glowing. And you can see that they glow with different colors. Well, we would like to measure the colors at which hydrogen and antihydrogen glow and determine whether or not these colors are identical. Now, what does this essentially mean? Measuring the colors that these things would glow at is, in some loose sense, equivalent to measuring how much time it takes of an electron to circle around the proton in a hydrogen atom, and measuring how much time or with what frequency a positron circulates around the antiproton in an antihydrogen atom. The rate or the frequency that they rotate around that is going to determine the color. And it could so happen that they rotate at different frequencies. In other words, it could happen that this positron goes around just a little bit faster than the electron goes around. If that was the case, the color emitted by these atoms would change. The antihydrogen would become more blue. Well, actually, these both emit in the ultraviolet, and it would become more ultravioletly, but I can't put ultraviolet up on the screen, so we'll just have to accept this analogy over here. Now, is this likely to happen? Well, no, according to one of the grand theories of physics. There's something called CPT symmetry, which I'll get into in a minute, and CPT symmetry is really one of the deepest things that we know. And according to CPT symmetry, the spectra of hydrogen and antihydrogen have to be the same. They could only be different if CPT symmetry is broken. Now, this is very, very unlikely. It really is. But it is worth studying, because proof that CPT could be broken would really revolutionize physics. It would surely be rewarded by a Nobel Prize. So what then is CPT? Well, I'm sorry, why should we use antihydrogen to look for CPT violations? Well, it turns out that one of the things that we can do most accurately is to compare the rate at which these electrons circle that proton and this positron circles the antiproton. It turns out that we can compare these so accurately that we could detect a difference of 1 part in 1 followed by 18 zeros. That's really an astonishing fact. In reality, these electrons go around, crudely speaking, about a quadrillion times per second. Imagine that, a quadrillion. It's a number that it's hard to even imagine how large that number is. If this positron was to go around just a little bit faster, so that after 1,000 seconds, it had gotten ahead by 1 full revolution. Remember, it's going around a quadrillion times per second. And I'm saying if this thing got ahead by 1 revolution in 1,000 seconds, that's something that in principle we could measure. So this is an incredibly sensitive test of whether or not they're going around at the same speed. Now, what exactly is the CPT symmetry that says that this can't possibly happen? Well, each letter in CPT stands for something that can be flipped. C stands for charge conjugation, P stands for something called parity conjugation, and T stands for time reversal. Now, consider the results of an experiment in which one of these things is flipped. Let's say I have an experiment over here, and I conduct an identical, almost, experiment over here, except I take everything, say, the charge in one of these experiments, and flip the charge. So over here, I had only minus charges. Over here, I had positive charges. Under some circumstances, the results of that experiment will be identical. And let me go into this in just a little bit more detail. For instance, let's take the C, charge conjugation. That says that the signs of all the charges are inverted. Positive charges become negative, negative charges become positive. Now let me do an experiment. Let's say I have 2 positive particles, 2 protons, and I have my fingers on these 2 protons, and then I suddenly let them go. What are they going to do? Everybody knows this. They're going to repel each other. They're going to go flying apart, right? Now, let's say instead I took these 2 positive particles and flipped their signs so that they both became negative particles. I have my fingers on them, and then I let them go. What's going to happen? Exactly the same thing. In other words, flipping the sign of the charge, at least in this experiment, results in the same net result. What about time reversal? Well, I've got a really neat demonstration that will show you time reversal over here. You've probably all seen versions of this. These are just 2 balls which are free to bounce back and forth. This one's particularly amusing because the balls are different. This ball weighs 3 times the amount that this ball weighs. Now, what I'd like to do is to let this light ball go, keeping the heavy ball stationary, and I want you guys to watch the pattern. All right, if you're a physicist, this is absolutely amazing, because what happens? After every other collision, the heavy ball is stationary. Let me start that up again. So here we go. I'm letting this one go. Stationary, 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 stationary. That's really kind of neat, at least if you're a physicist. This is an example of a collision. Collisions are really important in physics. There are all sorts of ways collisions come up in physics, and this is one of the important, this is one particular case. And it's possible for us to understand how this actually happens. We can apply the standard equations of conservation of momentum and conservation of energy, and we can solve for this system, and we'll get the right answer. And it will predict, indeed, that one of those balls will be stationary after every collision. But there's a much better way to do this. And the better way proceeds by taking a movie of that. And I've got a movie over here, and you can see this movie. It's slowed down a little bit. You can see that time is advancing on that clock over there. Okay, a movie of what you just saw in real time. Now, let's say I take that same movie and run it backwards in time. On the top is the original movie. You can see this clock is counting up in time. And on the bottom, I've just time reversed this thing. The clock is counting backwards. The movie's running backwards. And what I want you to see is that when you do this, it looks exactly the same. Everybody see that? The time reversed version of this experiment is exactly the same as the original version. And this is an example of T-symmetry, time reversal, in physics. I take an experiment, and somehow or other I get time to run backwards, and I get exactly the same result. The last letter in CPT symmetry is something called parity. Parity is a little bit more complicated. Could I have the lights back on here, please? But parity is best explained by gloves, 2 bicycling gloves in this particular example. One of them is a right-handed glove. The other one is a left-handed glove. Now, let's think about these 2 gloves for a minute. Is there any way that I can twist and turn this left-handed glove and turn it into a right-handed glove? All right. There's no way by simply moving it around and twisting it and turning it that I can turn my right-handed glove into a left-handed glove. But as somebody in the audience did say, to take a more worn-out glove of mine, if you take a right-handed glove and you turn it inside out, it becomes a left-handed glove, something that I've used on occasion when I've taken 2 right-handed gloves to a bike ride. So this is an example of a parity transformation. Actually, a better way of considering parity, a more physics way of considering a parity transformation, is to imagine looking at these 2 gloves and then just looking at one of them, but looking at it through a mirror. What's going to happen if I take a look at this glove through a mirror? Well, it's the same thing that always happens when you look at something through a mirror. Your right hand turns into your left hand. This left-handed glove is going to turn into a right-handed glove if I look at it in a mirror. And that's the parity transformation. If I take an experiment and turn everything that's right-handed into everything that's left-handed, wait, what do I mean by something that's right-handed and something that's left-handed? Well, there are gloves, but maybe something that's got a little more that's a little more familiar to you is sugar molecules. Those of you who are chemists or study chemistry or biology know that there are right-handed sugar molecules and left-handed sugar molecules, right? So the experiment consists of taking an experiment over here and taking everything that's right-handed and making it left-handed, and taking everything that was left-handed over here and making it right-handed, and running that experiment. And when you run that experiment, the results, at least under certain circumstances, will be identical. It doesn't matter that you did this parity transformation. Actually, parity transformations are discussed in the movie itself. They don't actually use this word, but there's a big discussion of it. Because in the movie, a big thing is made out of the logo for the Illuminati. And this logo for the Illuminati is what's called an ambigram. That's a real term, not invented by the book or the movie. The thing that's special about an ambigram is that if you rotate it by 180 degrees, it turns back into itself. Now, in the book, and presumably in the movie, there's this big mystical moments about this sort of thing. It's actually rather mundane from a physicist's point of view. We would call this a parity conserving rotational symmetry and a representation in the SO3 rotation group. But never mind. It's rather boring. A more interesting parity transformation would be a mirror reflection. Here I've taken the Illuminati logo and mirror reflected it. I'm just looking at it as if it was through a mirror. And you can see that there's no way for me to rotate this and get that. Okay, this is a fundamentally different object than these guys over here. This would be a mirror image. The transformation that takes this one over to this one is something that violates parity. Actually, you can have mirror images that don't violate parity. This is for the movie buffs out there. Here is a logo that appeared in a movie some years ago, back in 1985 actually, and it's a mirror ambigram. You can see that if I was to reflect this through a mirror, I would get exactly the same thing. Anybody know what movie this comes from? Back to the Future. This is the DeLorean Motor Corporation logo. Anyway, let's get back to CPT. So, what is it about CPT? As I said, each letter stands for something that can be flipped. Charge, parity, and time. And if we take some experiment and we flip all of the signs, minus becomes plus, we flip all the parity, left-handed becomes right-handed, and we turn time from going forwards to playing backwards, then the experiment that we do will be identical. Now, physicists really believe that this is true, that if you flip all of these three things, and you have to, as it turns out, flip all of these three things. If you just flip one of them, or if you flip some combination of two of them, you won't get exactly the same thing happening. But the CPT theorem says that if you flip all of these things, you will wind up back with exactly the same thing happening. On the other hand, yes?
Does the CPT theorem only apply to just a few particles, one or two at a time?
No, the CPT.
But in large systems, what about entropy increasing and finding the
That's above my pay grade. Entropy and time reversal and all of that are very complicated questions. I'd be happy to discuss it with you afterwards, but those are really, really hard, deep philosophical questions within physics. But it does apply to big systems as well as small systems. Okay. Why should we really bother? If everybody believes in the CPT theorem, it doesn't seem like there'd be much point to investigating this question of whether antihydrogen breaks the CPT theorem. But the fact of the matter is, there are outstanding problems there which do not seem to agree with the results of the CPT theorem. We exist because there's almost no antimatter in our universe. If there was a lot of antimatter in our universe, we would be blowing up on a regular basis. When we look out into the stars, we don't see any antimatter out there, and we can detect antimatter. We could detect antimatter if it was out there. We could detect it without too much problem. But it wasn't always that way. Back in the beginning, right after the Big Bang, the Big Bang, 14 billion years ago, should have produced equal amounts of matter and antimatter. And if I take some large amount of matter and combine it with some large amount of antimatter, the net result is it should all be gone. Everything should have annihilated. And yet, we know, unless this all is a figment of my imagination, that something was left behind, us. So of all of these particles out there, there must have been some sort of imbalance that resulted in us being left behind. Now, how could that have actually happened? Well, there's all sorts of ways people can speculate about it, but it seems likely that it didn't start out exactly balanced. There must have been just a little bit more matter than antimatter in the beginning, after the Big Bang. And nobody actually knows how to explain this. This is an open hole, an embarrassing thing in physics. We can't explain this. And maybe this is because CPT, which sort of guarantees, CPT and other theorems guarantee that they should be exactly balanced. Maybe they weren't exactly balanced. So it is worthwhile looking at these deeper questions, even if we expect that CPT probably is an okay theorem, is a correct theorem. So CPT and gravity studies both require antihydrogen. CPT probably requires trapped antihydrogen. Certainly precision gravity studies require trapped antihydrogen as well. Have we actually made any antihydrogen? The answer to that question is yes. The first antihydrogen atoms ever made, possibly the first antihydrogen atoms ever made in the history of the universe, were made at Lear in 1996. Lear was an accelerator, and they made about 9 of them, which isn't really that impressive. 99 more were made at the Fermi lab, but these antimatter atoms were made in a fashion that caused them to be traveling at about 90% of the speed of light after they were made. And it's fairly hopeless trying to study something that's going at 90% of the speed of the light, because it leaves your apparatus almost the instant it's created in the first place. So what physicists would really like to do is to create slow or trapped antihydrogen. And that's been done by this point, at first by the Athena collaboration at CERN in 2002, and very, very shortly thereafter by the ATRAP collaboration. Altogether, we've made on the order of 100 million antiprotons. Now, 100 million sounds like a lot, but it's really not. If they were tightly packed, they would form a box that was about 100 nanometers on a side. That's a box which is so small that we couldn't actually see that box. The whole net result would be that they would weigh 100 millionth of a gram, and if I was to use this as an energy source, it would be sufficient to run this laser pointer for about 1 second. So really, we haven't been able to make very much antimatter at all. In fact, we've made so little of it that it's very hard to detect that we've made it in the first place. This is an image of one of the first antihydrogen atoms, slow antihydrogen atoms, that was made and detected. What it is an annihilation event. There was an antihydrogen atom over here, which hit the wall of a trap, which generated 2 gamma rays going off in opposite directions, and some particles which are called pions, which go off in 4 more directions. These things were detected by particle detectors, which are these lit up boxes over here. Altogether, the sort of apparatus that it takes to detect that antihydrogen was made, the sort of detector that's necessary to detect that antihydrogen is made, costs on the order of $1 million. So you can see that if it costs us $1 million to make a detector that can detect antihydrogen, there's really no chance that we'll be blowing up the Vatican anytime soon. How do we actually do this? Well, we have to make an antimatter trap. And here's the antimatter trap from Angels and Demons. Here's a photograph of it. I don't know what our antimatter trap is going to look like in the end. I mean, we have some prototype traps now, but I'm absolutely certain it's not going to look like that. For one thing, we have to worry about how we would keep stuff inside of this trap. And we have to be able to make a bottle of antimatter in which the antimatter actually stays around. So what are the issues associated with getting it to stay around? Well, if there was any air inside of that trap, the antimatter would annihilate on the air, because eventually the antimatter would find particles of matter in the air and they would blow up, and that would be the end of it. So we have to be able to make a trap that has absolutely no air in it. Well, fine, you say. Some of you have worked in similar fields. You just take a big pump and you pump all of the air out. That turns out to be not even close to good enough. You have to do a lot better than using normal vacuum pumps to get out of the air. One of the things that you have to do is to cool the trap down. Inside here, I've got some liquid nitrogen. This is at 77 degrees Kelvin. It's very cold. I'm going to fill up this this little thing with liquid nitrogen. You can see it's boiling at this moment, and, but it will eventually stop boiling. Let's see if I can fill up the rest. And now I've got a nice little globule of liquid nitrogen. It's really cold. Just to show you how cold it is, I'll do a little demonstration. I've got a rose here. We're going to freeze this rose. I'm going to let it sit in there for a little bit. Anyway, we're going to have to take our trap, our bottle, and cool it down to temperatures which are even colder than the temperatures of liquid nitrogen. We have to get our trap down to temperatures of liquid helium. Because it turns out that when we really cool down our trap, all of the gas inside of that trap just condenses on the walls of the trap. And that's the only way that we can get a vacuum which is sufficiently cold, sufficiently good so that the matter doesn't annihilate. I think this is pretty cold by now. Let's see what happens with it. Rose petals. It got to be so cold that it just shattered when I slammed it against the table. Okay. So we have to make our trap really, really cold. And let me tell you, this trap of angels and demons doesn't look cold to me. That looks like it's at room temperature, so it's not realistic in that way. But there's another problem. Let's say we can get all of the air out. We still have to keep all of the antimatter from touching the sides of our bottle. Because after all, if it touches the sides of our bottle, it's going to annihilate. So we have to build a bottle which doesn't actually have any physical sides. How do you build a bottle out of nothing? The way you build a bottle out of nothing is to use electric and magnetic fields. And here's a picture of our trap. Basically what we have is we have a series of electrodes, and we put our antiprotons, p-bars is an abbreviation for that, in over here, and our positrons in over here. And we set up an electrostatic well, which is just basically a valley made with electric fields, and that traps the particles in the axial direction. It's a little bit harder to get them trapped in the radial direction, but I can show you how we do it with this demonstration over here, assuming this demonstration works, which, oh, yes, it is working. If you could zoom in on this at the moment, on this camera. I'm sure you guys can't see this in the back. Oh, what do I have to do here? I have to put this on auxiliary, right? Okay. Yeah. What you can see here, I hope, is right over here, is you can see a beam of electrons which is being emitted by an electron gun. And as you can see, that beam of electrons likes to travel in a straight line. And so it very quickly hits the glass, the sides of the glass over here. And basically, electrons get absorbed by the glass. In other words, these electrons are not trapped. However, I can use these coils over here to turn on a magnetic field. And the net result of turning on those magnetic fields is that that electron beam will be bent. I'm going to turn the electron beam on slowly, and you can see that I'm starting to bend that electron beam into a circle, and eventually I can get the beam to bend back onto itself. Well, this is how we can store charged particles in a trap without having them touch the sides. Basically, we apply a strong magnetic field. The particles all want to go out, but the magnetic field bends them around in a circle, and they come back to where they started. Let's go back to my presentation. How do we make antihydrogen? Well, Once we've got the particles in the trap like this, we somehow have to mix those particles together, and we can do that basically by electrostatically tilting the trap, and when it tilts, they just run into each other, and when they collide and overlap like that, they're going to make some antihydrogen. At this point, I could go into one of my normal seminar modes and start doing a lot of technology with you and a lot of physics with you, but I think it's inappropriate for the audience. So at this point, I think I'm going to leave how we actually do this, because it really does get quite technical very quickly, and just cover, in the very few remaining moments, a few other issues from the book. So, actually I'm a little bit early. Antihydrogen creation has been very successful. Our next step is to actually trap the antihydrogen atoms. That we have not succeeded in doing. So we can make antihydrogen, but we can't yet get them to stay within the bottle, and that's really the next step here. And with that, no, not quite with that, we're going to use, for those of you who are experts, we're going to use the antihydrogen magnetic moment to trap it in a minimum B field. And with that, I'd like to talk about some other issues within the book. According to the book, CERN owns an X-33 space plane. I don't know about this. I know that they have certainly not sent it to San Francisco to pick me up. They are, however, willing to send the shuttle to the airport to pick me up. In the book, CERN is a beautiful campus. And there is a beautiful building at CERN. This really is a very, very nice building. Actually, not only is this a very pretty building, it's a great architectural pun, because it's built to look like a cyclotron. Everybody see that? This outer thing here is this big magnetic coil, and this center cylinder in the center is this part of the building out there. So it's a great architectural pun. Unfortunately, it is not representative of the way the rest of CERN looks. CERN actually is rather run down, industrial. Here, for instance, is my beautiful office in a trailer. Do they have indoor skydiving at CERN? There's a scene in the book in which they have indoor skydiving. Much to my surprise, I talked to a friend of mine today who does parachute jumping. Indoor skydiving is real. There's a facility not far from here where you can go indoor skydiving. And I have a movie, I have a movie showing you indoor skydiving just for fun. It's about 10 seconds.
Say she ain't down with chick backstage when we in town. She like men on drum. She wanna hit and run. Yeah.
Anyway, the way that works, if I could have the lights back on, is there's a giant fan which blows people up, and you really can float on that if you know what you're doing. It costs something like a few $100 per a half-hour session, so it's not a cheap hobby, but you could do it. And a big point made of this in the book, that the facility to do this exists at CERN. How many people think that there actually is a facility to do this at CERN? Wait. These are my graduate students. They spent a lot of time at CERN, but obviously they've seen a part of CERN that sadly I have not. Anyway, I'd like to conclude by thanking a whole bunch of people. In particular, Roberto over here really helped me a lot with a lot of these demonstrations. But lots of other people have helped with me with this too. And I'm going to conclude by reading you a poem that was published in the New Yorker back in 1956, commemorating the discovery of the antiproton. Well up beyond the tropostrata, there is a region stark and stellar, where on a streak of antimatter lived Dr. Edward Antiteller. Remote from fusion's origin, he lived unguessed and unawares with all his anti-kith and kin, and kept macassars on his chairs. One morning, idling by the sea, he spied a tin of monstrous girth that bore 3 letters, AEC. Outstepped a visitor from Earth. Then, shouting gladly over the sands, met 2 who in their alien ways were like as lentils. their right hands clasped, and the rest was gamma rays. All right, it doesn't scan very well, but never mind that. Thank you very much for coming. I hope you've learned something about antimatter.